All right, welcome back to the deep dive. Today, we're going to tackle something that I think is pretty foundational, especially if you're shooting for that senior software engineer role. And that is, of course, static variables and methods.
Yeah, you definitely run into these guys a lot.
Oh, yeah. And, when you hit those senior level interviews, having that deep understanding of, you know, not just what they are, but like really why they matter in the grand scheme of system design, it can make a big difference.
Absolutely. I mean, it's all about, being ready for those really in-depth technical discussions. Like, we're going to really dissect these static members today, figure out what they are, how they work, and kind of what to watch out for when you're using them.
So, like, we've all seen the term static,
Yeah.
right? But honestly, sometimes it feels a little bit, I don't know, maybe misleading.
Yeah, I get that.
Like, I've even heard some folks suggest that class variable might actually be a more intuitive way to think about static variables. Like, it puts the emphasis on the fact that this variable isn't tied to a specific object, but to the class itself, right? The blueprint.
That's a really good point. Like, thinking of it as a class variable really helps you wrap your head around it at first. It makes it clear that this thing belongs to the class as a whole, not just one of the objects that you create from it.
Okay, so let's get down to brass tacks here, starting with static variables. So the main idea is that if you have a variable that's declared as static inside a class, there's only one copy of that variable, no matter how many objects you make from that class. It's like this shared resource that all those objects can access and potentially even change.
Exactly. Now think about that compared to the usual instance variables that you see all the time. Every time you make a new object, it gets its own separate copy of each instance variable. But static variables, they're different. They're attached to the class itself, not to any specific object.
Okay, so let's imagine a real-world situation here. Like, let's say we need to create unique IDs for employees, right? We've got this employee class.
Right.
So we could have a static variable, let's call it lasted, and start it at 0. And then every time we create a new employee object, we increase this lasted and use that new value for the employee's own id. That way, every employee is guaranteed to have a unique ID.
Makes sense. And that's a simple way to do it. But remember, you're basically introducing this global, mutable state into your application. In really big, complex systems, managing that can get kind of tricky.
Right.
You might end up using more advanced design patterns or different strategies to handle that, like maybe even a dedicated ID generation service, especially if you need to deal with a lot of things happening all at the same time.
Yeah, concurrency is definitely something you've got to consider, especially as a senior engineer. Like, if you've got multiple processes trying to create employee objects at the same time, that simple approach of just increasing last IC could cause problems, right? You could end up with duplicate IDs, and that's a mess.
Yeah.
It just goes to show that when you're dealing with things that could be changed by multiple processes at once, you really have to be careful.
Oh, for sure. It seems simple on the surface, but the way a static variable acts when you've got lots of things happening at once, it really highlights how important it is to make sure things are thread safe and synchronized, especially when you're working with shared resources.
Okay, so we've talked about mutable static variables, but what about static constants? Those seem to be way more common in the real world. You declare those using both the static and the final keywords, right?
Right, and that final keyword is super important. It means that once you set a value for a final variable, it can't be changed. So with static final, you're basically saying this is a constant value that's shared across the entire class, and it's never going to change.
Right. Like, take the classic math class, for instance. It has PI defined as public static final double PI equal 3.14159. And it makes perfect sense, right? Pi is a universal constant. Its value is always the same no matter where you are. You don't need to create a math object to use it.
Yeah, exactly.
Now, let's flip that for a second. What if PI was an instance variable? Would that be a good idea in a large application?
Well, think about it. Every single math object you create would have its own copy of pi, which is completely pointless and wastes memory, right? But even more importantly, making it an instance variable goes against the whole idea of pi being a constant. You wouldn't want different math objects potentially having different values for pi, even if it's just theoretically possible. That static final declaration ensures there's just one unchanging value, and it belongs to the class itself.
Okay, so now let's say we've got a static final variable. It's not a simple type like a number, but an object. For example, in our employee class, we might want a static final random generator to create random numbers. What are the potential downsides of sharing this generator across all instances?
That's a really good question. Sharing a single random object can definitely be more efficient than creating a new one every time you need a random number. But you could run into problems if you're not careful. For instance, if different parts of your application are all using the same generator, the sequence of random numbers could become predictable. And that could lead to unexpected issues, especially if you're dealing with things like security, where randomness is super important.
Right, so in those situations, you might actually want to use separate random generators with different seeds to make sure things are truly random.
Exactly.
And of course, we can't forget about the classic System.out, which is a public static final print stream out in the system class. I mean, we use System.out.println all the time.
Hmm.
Since out is static, we can just access it directly without having to mess around with creating a system object.
Yeah.
And since it's final, we normally can't change what it points to.
Although there's this kind of weird thing in Java with the system.setOut method. It's one of those native methods, meaning it's not actually written in Java. It does its thing outside of Java, probably in the operating system's libraries. And this method can actually override the final restriction and make system.out point to a different output stream.
Interesting.
It's kind of like a leftover from the old days and not something you'd typically use in your everyday coding.
All right, so we've seen how to declare and initialize simple static variables. But sometimes you need to do more complex setup, right?
Mhm.
That's where those static initialization blocks come in.
Exactly. Sometimes you just can't initialize a static variable with a simple assignment. You might need to do some calculations or set up a collection. Static initialization blocks let you handle those more complicated cases.
Like, think about a credit card form. Let's say you need a list of all the valid expiration years for that form. Instead of creating and filling that list manually, you could use a static initialization block. This block would figure out the current year, calculate the next 20 years, and then add all those years to a static array list called, let's say, expiration year. That way, you know the list is set up correctly as soon as the credit card form class is loaded.
What's really important to understand is that this static initialization block only runs once. When the class is loaded for the first time, that's it. It doesn't matter how many credit card form objects you create after that. That expiration year list is already set up at the class level.
Right. And it's important to remember that if you don't explicitly initialize a static variable, it's going to get a default value, like 0 for numbers, false for booleans, and null for objects. So if you need anything more complex than that, static initialization blocks are your friend.
And don't forget that the order you declare and initialize things in actually matters. Static variable initializers and static initialization blocks, they all run in the order they appear in your code. That can be important if you have dependencies between your static variables or within your initialization logic.
All right, let's move on to static methods. Just like static variables belong to the class, so do static methods. They don't act on specific objects, just on the class itself.
Right. A classic example is the Math.PI x method. It takes a number x and raises it to the power of a. It doesn't need any information from a specific math object to do its thing. It's just a general purpose function that logically belongs to the math class as a whole.
Which brings up an interesting design point. Why is POW a static method and not an instance method, maybe on the double type itself?
Well, in Java, primitive types like double aren't actually objects. They don't have methods like classes do. You could theoretically make POW an instance method of the math class, but that would force you to create a math object every time you wanted to calculate a power. And that seems kind of wasteful, right?
Mm-hmm.
It doesn't really fit the idea that the operation itself doesn't rely on any specific object's data. So for things like utility functions that are essentially stateless, static methods just make more sense. They're cleaner and more logical.
And another common use for static methods is to add functionality to existing classes, especially ones that you might not be able to change directly, like classes from standard libraries. For example, we might have a random numbers class with a static method next random generator, int, low, and high, to generate a random integer within a certain range using an existing random object. So what are some of the reasons you might create a separate utility class like that instead of, just adding those methods directly to the random class if you could?
That's a really important question when you're thinking about organizing your code and sticking to good principles like the single responsibility principle. Having a dedicated utility class like that can be a good idea if you have a bunch of related functions that extend what another class can do, but aren't really core to what that original class is supposed to do. In the case of random, its main job is to generate random numbers. Adding stuff for specific ranges might be considered a secondary concern. So by putting those functions in a separate utility class, you keep random focused on its core job while still providing those extra functions in a well-organized way. It also makes it easier to reuse that random numbers class in different parts of your application without tying them directly to the random class itself.
Right, so it's all about modularity and keeping things clean. Now, I know it's technically possible in Java, but why is it generally considered bad practice to call a static method using an object instance? Like, if you had a local date object called date, you could write date.now, but the correct way is local date.now. What's wrong with doing it that first way?
Even though it'll work, calling a static method on an object can be confusing for other people reading your code. The now method is static, meaning it operates on the class as a whole. It doesn't need any information from a specific local date object. So when you call it on an instance, it looks like you're using data from that specific object, which isn't actually happening.
Right.
It's just not clear and can make your code harder to understand. It's always better to be explicit and accurately reflect what the code is actually doing.
Makes sense. Just a quick reminder, static methods can access static variables within their own class, but they can't directly touch instance variables. I mean, that makes sense logically, right?
Of course, a static method isn't tied to any particular object. It has no idea which object's variables it should be using. Instance variables are specific to each object, while static methods work at the class level, independent of any specific object.
Okay, let's talk about factory methods now. This is a super important concept, especially for those tough senior level technical interviews. Factory methods are basically a way of using static methods to create objects in a more controlled and flexible way.
Exactly. A factory method is just a static method inside a class that gives you back a new instance of that class, or maybe even a subclass. It's a more sophisticated way to create objects compared to just using constructors directly.
And a perfect real-world example is the number format class in Java, with methods like numberFormat.getCurrencyInstance and numberFormat.getPercentInstance. When you call these methods, they give you back special number format objects that are all set up to format numbers as currency or percentages based on the current locale.
The beauty of factory methods is that they give you a lot of control and flexibility when you're creating objects. Unlike constructors, which can only create instances of their own class, factory methods can create instances of subclasses.
That's interesting.
Plus, they usually have more descriptive names, which makes it easier to understand what kind of objects you're getting. Take the number format example again. Get currency instance and get percent instance tell you exactly what those methods do. You couldn't achieve that same level of clarity with just constructors, especially if they had the same parameters.
Right, that makes sense. Like, imagine you have an interface and you want different implementations of it depending on some configuration. A factory method could handle that logic behind the scenes and give you back the right implementation without the calling code needing to know all the details.
Exactly. It's all about programming to an interface, not an implementation. Factory methods can also hide the specific classes being created from the client code, which is a good thing.
All right.
And another neat trick is that factory methods can even return objects that have already been created. This is super useful for things like singletons, where you only want one instance of a class to exist, or for managing resources efficiently.
All right, so let's recap. We've explored static variables, which only exist once per class, and static constants, which are perfect for those unchanging shared values. We dug into static initialization blocks for those times when you need to do more complex setup when a class is loaded. And we took a deep dive into static methods, seeing how they're used for utility functions and, most importantly, as factory methods for creating objects in a more elegant way.
Knowing this stuff inside and out is absolutely crucial for any senior software engineer. It's not just about memorizing definitions, it's about understanding the whys and hows. Why would you use a static variable or method? When does it make sense? What are the trade-offs, especially in a multi-threaded environment? And how do they all fit into good object-oriented design? Being able to explain all of this clearly and with relevant examples is super important during those senior level technical discussions.
So, as you're wrapping your head around everything we've talked about today, here's a question to think about. In the projects you've worked on, were there any places where you could have used static methods or variables to improve the design, make the code more efficient, or just make it simpler? What are some of the potential challenges or gotchas you might face when using static members in really large, complex systems? Think about that, and thanks for joining us on The Deep Dive.